All right, everyone. In this video, we are going to look at a brand new integration technique called integration by parts. Now, if we imagined that substitution, our last method of integration, was undoing the chain rule, then integration by parts can be thought of as undoing the product rule. So recognizing when we can take an antiderivative, thinking in terms of the product rule, and undoing it. So let's start by returning to the product rule. What was the product rule? Well, the product rule said, as we see here, that if we have a product, f times g, and we wanted to take the derivative of it, we would end up with f prime times g plus g prime times f, right? Our end result would be a sum of two different expressions, and each of those expressions would have an f and a g with the derivative hitting one of them. So in the first one, f prime times g, and in the second one, g prime times f. Now, this statement, this entire statement up here, can be transformed into an equivalent statement using the language of antiderivatives and integrals. And we see that down here. Namely, we're going to take each of our two pieces, the f prime times g and the g prime times f, and we'll say that the antiderivative of each of those together is equivalent to the antiderivative of the derivative of f times g. So that's just f times g plus a constant c. And maybe just to clarify, to get from one line here to the other, I said it's the equivalent reframing, and it is. But you could also think of it as throwing a big old integral sign on both sides of this expression, right? And you'll notice that the right-hand side, the integral of f prime times g plus g prime times f, I've split that into two pieces. So the integral of f prime times g, and then plus the integral of g prime times f. And so the original right-hand side, I've now just rewritten distributed on the left-hand side. And meanwhile, this other piece, we have the integral of a derivative of f times g. And so that will just give us f times g, right? The integral and the derivative will cancel each other out by the fundamental theorem of calculus. And so we'll just be left with f times g plus a constant. So this new method of integration by parts is going to take advantage of this relationship. And we're going to think about it as follows. I guess maybe I should say first, let's rewrite this one more time. I'm going to leave this g prime times f of x dx on the left-hand side of the equation, but I'm going to rewrite it just as the integral. I'm just going to flip the order of these. So I'm just going to rewrite this as f times g prime of x dx. And then I'm going to take this other piece and I'm going to subtract it to the other side of the equation, right? So I'm going to move this to the other side of the equation, the other side of the equal sign, but it's going to have a negative sign on it because I've subtracted it over. So we're going to get f of the integral of f of g of x. The integral of f times g prime is equal to, and then I'm still going to have on the right-hand side my f times g, but now I'm going to be subtracting, and then this piece in the left, in the light blue, subtracting the integral of g of x times f prime of x dx. And we could include this plus c if we wanted to. I'll note, though, that as the part of taking this antiderivative on the right-hand side, that will automatically include a plus c. So this plus c, I don't actually care about whether I keep it in there or not for the moment, sort of take it or leave it. But this is the core formula that is going to be used for the integration by parts. So specifically, to use this formula, I want to basically take this formula, but I'm going to let the f of x expression be replaced by a u. And using our convention from u substitution, if f of x is u, then the expression f prime of x dx can be thought of as an expression du. And similarly, if I'm going to let my g of x be thought of as a v, then my g prime of x dx, I can think of that as a dv. And we get this formula down here. I guess, again, f is a u and g is a v. And so we're going to get this really slick formula in which the integral of an expression that looks like u dv is equivalent to u times v minus the integral of an expression v times du. Now, this is a sort of shorthand formula in what we'll call our integration by parts formula, but this is being used to represent an expression like the one up here. And specifically, our goal is to use this formula by looking at an initial integral and identifying a good choice of u and dv. And now we will talk about what makes a good choice of u and what makes a good choice for our dv. But let's start just by looking at one example. And this is the example of the integral of x times sine of x dx. Now, my goal for the moment is to recognize this expression as an expression u times dv for an appropriate choice of u and dv. Once I do that, I can identify my u, I can identify my v, and I can use the formula up here to calculate this integral. So let's give this a try. And again, we'll talk about strategies for choosing a good u and a good dv. But for now, I'm going to suggest that just letting u equal x is a good choice. So u equals x is a good choice. And that leaves dv to be the sine of x dx. All right, so that's going to be my choice of u and my choice of dv. Now, corresponding to these, we're going to need to also choose, or we're going to need to identify a du and a v, right, to use this formula up here. And remember, the relationship between u and du and the relationship between v and dv is the relationship between a function and its derivative. So u was a function f, and du corresponds to its derivative, f prime, specifically du equals f prime of x dx. And similarly, dv, if dv is a g prime of x dx, then v is just g. We find it by taking an antiderivative. So to go from u to du, we'll take a derivative. And to go from dv back to v, we'll take an antiderivative. In other words, if our u is this expression x, then our du has to be the derivative of that, which is just 1 dx. And if our dv was sine of x dx, our v should be an antiderivative of sine, which is going to be negative cosine. Again, I could include a plus c here, but I don't. I'm gonna skip that for now. We'll include a plus c at the end of this process. But now, with this choice of u and this choice of dv, I have an expression for du and an expression for v, and I can use the integration by parts formula that I have up here. And so again, that is just going to say that the integral of u dv, which was x times sine of x dx, is going to equal u times v, So that's x times negative cosine of x minus an integral of v du. So that's minus an integral of negative cosine of x du, which is just 1 dx. And so we get an answer for our original integral that has, at least for the moment, another integral in it. So rewriting this, this is just negative x cos x minus a negative integral of cosine. And so this is a complete and correct answer, but it can be made even stronger by recognizing that we can calculate this new antiderivative. And so we get the antiderivative of x sine x is going to be x cosine of x plus, and now this antiderivative is just sine of x plus c. And that gives us a complete and correct answer for this antiderivative. So this is the method of integration by parts, recognizing that the integral we're trying to compute is one part of a product rule, and coming up with a systematic way to use that fact to find a full antiderivative, specifically by identifying a good choice of u and dv. In the future, we'll talk about how to choose our u and dv, and we'll get a lot of practice doing this work. But that's going to do it for this video. Thanks so much for watching, and see you next time.